Part 1. The message came to Earth on a Tuesday morning, and it changed everything humanity thought they knew about their place in the universe. Senior Architect Al of the Galactic Union's Architect Collective had spent 3 standard cycles debating whether to send it. The collective was the most respected engineering organization in known space. They had built wonders that lesser species could not even imagine. They had constructed orbital rings around gas giants, space elevators that stretched across entire star systems, and habitat spheres that housed trillions of beings in perfect comfort. They did not ask for help. They certainly did not ask for help from a species that had only achieved faster-than-light travel 80 years ago. But the Lattice Project had broken them. The structure was supposed to be their greatest achievement, a network of energy-collecting platforms arranged around a binary star system, capable of harvesting more power than most civilizations used in 1,000 years. The mathematics were perfect. Al had checked them personally, and their crystalline body was literally made of living mathematics. Every calculation was correct. Every material was properly. Every stress point was accounted for. And yet every simulation ended the same way. Catastrophic collapse within 300 cycles of activation. The lattice would twist, buckle, and tear itself apart. No matter what they changed, no matter what they adjusted, the result was always the same. Al had consulted the finest minds in the Union. They had examined the quantum mathematics and found no errors. The collective's own internal review had studied the design for an entire cycle and declared it perfect. The mechanical priests of 7 had blessed the blueprints according to their ancient rituals, which, despite sounding foolish, had a proven track record of identifying structural flaws. Nothing worked. The design was perfect and it would not function. That was when someone, Al could not remember who, had mentioned the humans. The suggestion had been met with silence at first, then gentle dismissal. Then, as the project deadline approached with no solution in sight, reluctant consideration. The humans were strange. Everyone in the Union knew this. They came from a death world where the very environment tried to kill them constantly. Their biology was chaotic and messy. Their social structures made no logical sense. And their engineering was the subject of whispered conversations at academic conferences. Tales told by trade vessel crews who had visited human space and returned with expressions of confused horror on their faces. Human ships that flew despite having engine configurations that violated fundamental principles of physics. Human buildings that stood for centuries despite being constructed with what the architects would consider criminal levels of imprecision. Human bridges that swayed in the wind but never fell, while perfectly rigid collective designs shattered at the first unexpected stress. There was a human concept that had begun spreading through the Union's engineering schools, whispered by students who found it either fascinating or terrifying. The humans called it good enough. It was, according to the architect's understanding, the idea that something did not need to be perfect to work. It only needed to be adequate for its purpose. The concept made Al's crystalline matrix itch. But desperation was a powerful motivator, and so the message was sent. The human delegation arrived 3 weeks later aboard a ship called the Hamilton. Al's deputy, a younger architect named, had scanned the vessel as it approached Architect Station 9. The results had nearly caused their crystalline structure to crack. Senior Architect had said, their voice wavering with something that might have been fear, this ship should not be capable of faster-than-light travel. Al had examined the scan data personally, was correct. The engine configuration was wrong. The power distribution was wrong. The hull geometry was wrong. According to every principle the collective held dear, the Hamilton should have torn itself apart the moment it attempted to enter hyperspace. And yet there it was, docking with the station, its crew apparently unaware that their existence was a mathematical impossibility. The human captain, a tall man with a beard and a relaxed smile, had noticed staring at the ship's engine readings during the welcome ceremony. "Something wrong?" he had asked. "Your engines," had managed. "They should not work." The captain had glanced at the readings, shrugged, and said, "Yeah, we know. We just kind of ignored that part." Then he had walked away to greet the rest of the welcoming committee, leaving frozen in confused distress. The human engineering team consisted of 12 individuals. Their leader was a woman named, small in stature with gray-streaked hair and sharp eyes that seemed to see more than they should. She wore a formal jacket that someone had attempted to clean, but which still bore visible stains from what Al later learned was something called motor oil. Her team was equally confusing. They carried devices that the collective sensors could not properly classify, battered notebooks filled with handwritten calculations, small metal tools of archaic design, rolls of a gray adhesive material that the humans referred to simply as duct tape, though they refused to explain what a duct was or why it required its own specialized tape. Al greeted them formally in the station's main conference chamber, a vast space of perfect geometric proportions designed to inspire awe and respect. "We are grateful for your assistance," Al said, though the words felt strange coming from their speaking crystal. The collective had never been grateful for outside help before. "The problem we face has proven beyond our ability to solve." Nodded politely, but Al noticed her attention was not on them. She was looking at the walls, the ceiling, the floor. Her eyes traced the perfect angles and the flawless surfaces with an expression that might have been curiosity or might have been concern. "Nice place," she said. "Very clean, very precise." She paused. "How old is it?" "This station was constructed 400 cycles ago," Al replied. "It has required no significant maintenance in that time." "None at all. Our construction methods do not require maintenance. Everything is built to exact specifications. There is no degradation, no wear, no need for repair." Exchanged a glance with one of her team members, a large man named David who had remained silent until now. Something passed between them, some understanding that Al could not interpret. "Interesting," said finally. "Show us the problem." Al led them to the simulation chamber, where the lattice project was displayed in perfect holographic detail. The structure hung in the center of the room, rotating slowly, every platform and connector and support beam visible in precise miniature. "This is the lattice," Al explained. "The design is correct. The mathematics are correct. Every component is exactly as it should be, and yet it fails. Every simulation shows collapse within 300 cycles." They ran the simulation. The humans watched in silence as the lattice began its operation, collecting energy from the twin stars it surrounded. For a time, everything functioned as intended. Then, gradually, stresses began to build. Small deviations accumulated. Vibrations resonated through the structure in unexpected ways. And finally, catastrophically, the lattice twisted and tore itself apart. "We have made 947 adjustments to the design," Al said. "None have resolved the issue. The mathematics remain correct. We do not understand why it fails." Studied the frozen image of the destroyed lattice for a long moment. Then she turned to face Al directly. "Your problem," she said, "is that you're building it correctly." Al waited for further explanation. Their crystalline structure hummed with confused anticipation. Surely the human would elaborate. Surely she would explain what she meant by such a contradictory statement. Just smiled slightly and turned back to the hologram. "We're going to need access to all your simulation data," she said, "and somewhere to work, somewhere we can make a mess." Made a small sound of distress at the word mess. "Also coffee," said David, speaking for the first time. "Lots of coffee." Al did not know what coffee was, but they had a feeling they were about to learn many things they did not know. "You will have everything you require," they said. "But I must ask, what did you mean when you said we are building it correctly? How can correctness be the problem? Smile widened slightly. It was not a reassuring expression. That's what we're going to show you, she said. But I'll warn you now, you're probably not going to like it. She was right. Al did not like it at all. Part 2. The first thing the humans did was make a mess. They had been given a pristine workspace adjacent to the simulation chamber, a room of perfect white surfaces and carefully organized equipment. Within 3 hours, it was unrecognizable. Cables stretched across the floor in tangled patterns. Pieces of paper covered with hand-drawn diagrams were stuck to every available surface. Empty containers from something called instant noodles were stacked in a corner. The gray adhesive tape had been applied to at least 7 different objects for reasons that no one had explained. Had visited the room on the second day and had to be escorted away after their crystalline structure began vibrating at a dangerous frequency. The visual chaos was physically painful to them. Al forced themselves to observe without judgment. The humans were here to help. Their methods, however disturbing, might contain wisdom that the collective lacked. This was the thought Al repeated continuously, like a meditation, whenever they witnessed something that made their mathematical core want to recoil in horror. Had divided her team into groups. Some were studying the simulation data. Others were examining the material specifications. A few were doing something they called back-of-the-napkin calculations, which involved writing numbers on small pieces of absorbent paper rather than using proper computational equipment. On the third day, called a meeting. "Okay," she said, standing before a wall covered in paper and connected by lines drawn in colored ink. "Here's what we've found. Your design is perfect. Mathematically speaking, it's the most elegant megastructure blueprint I've ever seen. Every angle is optimal. Every material choice is ideal. Every stress distribution is calculated to absolute precision." Al felt a small glow of pride. Their work was being recognized. "That's your problem," continued. The glow faded quickly. "I do not understand," Al said. "You are saying that perfection causes failure." "No, I'm saying that perfection doesn't leave room for reality," pointed to one of the paper diagrams. "See this. Your load calculations assume that every component will perform exactly as. Every beam will have exactly the strength your math predicts. Every joint will align precisely as designed. Every force will travel exactly where you expect it to go. Yes, this is correct engineering. It's correct theory, but reality doesn't work that way." Pulled down another piece of paper. "In the real universe, materials have variations. Manufacturing has tiny errors. Stars don't behave exactly as predicted. Gravity fluctuates. Cosmic radiation causes unexpected degradation. A million tiny imperfections accumulate over time." David stepped forward. He was holding a piece of metal that he had apparently brought from the human ship. "This is a structural beam from our vessel," he said. "Look at it closely." Al examined the beam. Its surface was covered in tiny scratches and marks. There were visible variations in its thickness. The crystalline structure of the metal itself was irregular, with small inclusions and impurities scattered throughout. "This is very poor quality material," Al observed. "This is the same material we use in all our ships," said. "It's been in service for 30 years. It's never failed." "How is that possible? The imperfections should cause stress concentrations. The material should have fractured long ago." "That's what your calculations would predict. But those imperfections actually make it stronger. The variations in the crystalline structure stop cracks from spreading. The slight irregularities in thickness allow flex instead of fracture. The material can absorb unexpected stresses because it wasn't designed to handle only expected ones." Al's mathematical core struggled with this concept. It was like being told that errors improved accuracy or that ignorance enhanced knowledge. The logic simply did not connect. Seemed to sense their confusion. "Let me try another explanation," she said. Your lattice is designed so that every force has exactly one path to follow. If everything goes exactly as planned, those paths work perfectly. But if anything goes wrong even slightly, there's nowhere for the stress to go. It builds up until something breaks. And when that thing breaks, all the stress that was going through it has to go somewhere else. But there's no somewhere else. So the next component breaks, and the next. And suddenly your whole structure is tearing itself apart. She drew a simple diagram, a line of circles connected by single lines. This is your design. One path, perfect efficiency, zero redundancy. Then she drew another diagram, a web of circles connected by multiple intersecting lines. This is how we build things, multiple paths, less efficient. But when one path fails, the stress flows to others. The structure bends instead of breaking. It adapts instead of collapsing. You are describing intentional imperfection, Al said slowly. We're describing resilience. There's a difference. One of the other human engineers, a young woman named, stepped forward with a tablet displaying historical data. In 1940, on our home planet, there was a bridge called Tacoma Narrows, she said. It was designed with perfect efficiency. Every component was calculated to handle exactly its expected load. When wind hit it at a certain frequency, it began to vibrate. The vibrations built up because the rigid design couldn't absorb them. Eventually, it tore itself apart. She showed a recording. Al watched in horrified fascination as the bridge twisted and writhed, its perfect geometric form distorting into impossible shapes before finally collapsing into the water below. After that, we changed how we designed bridges. We added flexibility. We included components that could absorb unexpected forces. We built in redundancy so that if one part failed, others could take over. Our bridges became less mathematically elegant but much harder to destroy. You learned to build imperfectly on purpose, Al said. We learned to build for reality instead of theory, replied. The concept was deeply troubling. Everything the architect collective believed was based on the pursuit of perfection. Their entire civilization was built on the principle that correct calculations led to correct outcomes, if this principle was flawed. But Al could not deny the evidence before them. The human ship that should not fly, the human beam that should have broken, the human bridges that survived while perfect structures failed. What do you propose? They asked finally. Smiled. It was still not a reassuring expression. We're going to teach your lattice how to fail, she said. Over the following weeks, the humans systematically dismantled everything the collective believed about engineering. They introduced a concept called tolerance's intentional imprecision in measurements. Instead of specifying that a beam should be exactly 100 units long, they suggested specifying that it should be 100 units long, plus or minus a small amount. This small amount, they explained, allowed for real-world variation without causing failure. Asked how they determined the size of the tolerance. Experience mostly, said, also gut feeling. What is gut feeling? It's when you look at something and your stomach tells you whether it's right or wrong. Your digestive organ has engineering expertise. More than you'd expect, honestly. They introduced safety factors, deliberately overbuilding components beyond their expected requirements. A beam that needed to support 100 units of load would be built to support 250 units instead. This is wasteful, protested. You are using more than double the material needed. Yes, that's why it works. But the efficiency loss is worth it when something unexpected happens, and something unexpected always happens. They introduced failure modes, deliberate weak points designed into the structure so that if something did break, it would break in predictable, manageable ways rather than catastrophic ones. You are building in the expectation of failure, Al observed. We're building in the ability to survive failure, corrected. Big difference. The most disturbing proposal came near the end of the second week. Suggested adding what she called deliberate flaws to the lattice's primary junction points, microscopic imperfections in the material structure that would allow the components to flex in ways the original rigid design prohibited. "You want us to introduce errors," Al said, "into load-bearing components, the most critical parts of the entire structure." "They're not errors, they're features. Your current design is like a steel rod, strong, but when it bends past its limit, it snaps completely. What we're suggesting is more like a rope. It flexes, it stretches, it absorbs force instead of resisting it absolutely. A steel rod is stronger than a rope. A steel rod breaks and becomes useless. A rope survives and keeps working. Which matters more, peak performance or continued function?" Al had no answer. The simulation chamber hummed as the modified design was tested. Stood with her team, watching the holographic lattice rotate slowly in the center of the room. "Run it," she said. The simulation began. The lattice collected energy from the twin stars. Stresses built as before. Vibrations resonated through the structure. The same conditions that had destroyed every previous iteration. But this time, something different happened. The junction points flexed. The redundant pathways redistributed stress. The tolerances allowed components to shift slightly without triggering cascade failures. The structure wobbled, adjusted, and stabilized. 300 cycles passed, then 400, then 500. The lattice held. "That's impossible," whispered. "No," said quietly, "that's engineering." Part 3. The lattice went operational 4 cycles later. Al watched from the observation deck of the construction oversight vessel as the final components were placed into position. The structure was enormous, spanning the space between 2 young stars, its platforms and connectors and support beams stretching across distances that would take light itself several minutes to cross. It was not beautiful, not by collective standards anyway. The old design had been elegant, symmetrical, mathematically perfect in its form. This new design was different. There were irregularities visible even from this distance. Components that did not quite align, connections that curved where they should have been straight, redundant pathways that added mass and complexity without adding function. It looked, Al thought, reluctantly messy. It also worked. The first stress test came in the second month of operation. A solar flare from the larger of the 2 stars sent a wave of charged particles through the lattice that no simulation had predicted. In the original design, this would have caused a cascade failure starting at the 3rd ring of collectors and spreading outward until the entire structure collapsed. In the new design, the affected collectors flexed. Their junction points absorbed the unexpected energy. The backup pathways routed power around the damaged sections. 17 components failed completely, and the lattice did not even pause its operations. Repair drones replaced the failed components within a week. The lattice continued functioning as if nothing had happened. Reported the incident to Al with an expression of confused wonder that the young architect would wear frequently over the coming years. "The structure survived a Class 7 flare event," said. "The original design would have been destroyed. This one barely noticed." "What is the status of the failed components?" "Replaced. The lattice routed around them automatically during the repair period. We did not even need to reduce power collection." Al nodded slowly. They had expected this. The humans had warned them, but expecting something and experiencing it were very different things. "Prepare a report for the Central Archive," they said. "Full documentation of the incident and the structure's response. Do not alter any details to preserve our reputation." Hesitated. "Senior architect, the report will show that the original collective design failed where the human-modified design succeeded. This will be embarrassing." "It will be accurate, that matters more." The report was filed. It caused considerable discussion in the collective's governing councils. Some members argued that the incident was an anomaly, that the original design would have functioned properly under normal conditions. Others suggested that the human modifications had introduced dangerous instabilities that would manifest over time. But as the months passed and the lattice continued operating, surviving stress after stress that would have destroyed its predecessor, the arguments faded away. The evidence was too clear to ignore. And her team returned to Earth after the lattice went operational. Al met with her before she departed. "You have taught us something valuable," they said, "something we did not want to learn." Smiled her unsettling smile. "And what's that?" "That perfection is not the same as effectiveness, that correct calculations do not guarantee correct outcomes, that the universe does not care about our mathematics." Al paused. "These are difficult truths for my people." "They were difficult for us too once. We had to learn them the hard way. Bridges falling, ships sinking, rockets exploding. Every failure taught us something new about how reality actually works. We have avoided such failures. Our methods have always produced functioning results." "Have they? Or have you just been building things that don't push against the edges of what's possible?" Gestured toward the viewport, where the distant lattice was visible as a faint geometric pattern against the stars. "That structure out there is the most complex thing your species has ever built. It works because you finally admitted that you don't know everything, that you can't predict everything, that you need to build for surprises, not just for expectations." Al considered this. Their crystalline structure hummed with something that might have been discomfort or might have been growth. It was difficult to tell the difference. "Will you return if we need further assistance?" "Probably. We humans have a saying, 'It's not stupid if it works.' You've got a lot of projects that are very smart and don't work. We're pretty good at making things less smart and more functional." After the human delegation left, the Galactic Union's Engineering Standardization Committee held an emergency session. The lattice incident had raised questions that could not be ignored. If the collective's methods were flawed, what else might they be wrong about? The debate lasted for several cycles. Eventually, a compromise was reached. A new category was added to the Union's official engineering documentation. It was called Terran Methodology, and it was defined, after much argument, as engineering approaches that function despite theoretical impossibility. The definition was controversial. Many architects found it insulting to their profession. How could something be theoretically impossible yet still function? It was a contradiction in terms. It was nonsense. But the lattice continued operating. Human ships continued flying. Human structures continued standing. And slowly, reluctantly, the Union began to accept that their understanding of engineering was not as complete as they had believed. Human consultants became increasingly sought after in the cycles that followed. Not for elegant solutions, the collective still excelled at those. Not for theoretical breakthroughs, other species handled pure research better. Humans were called when something should work but did not, or when something should not work but needed to anyway. They developed a reputation, not as the engineers in the galaxy, or the most sophisticated, or the most mathematically rigorous. They were known as the species you called when you had given up on doing things properly and just needed them done. This was, the humans assured everyone, meant as a compliment. Back on Earth, returned to teaching. She had been an educator before the collective's invitation, and she returned to it gladly. Her students at the Advanced Engineering Institute were young people who would someday build the next generation of human achievements. She wanted to make sure they understood what that meant. Her first lecture always began the same way. "The universe has rules," she would say. "Physics, mathematics, thermodynamics. We study these rules because understanding them helps us build things that work." She would pause, looking around the room at the eager young faces. "But here's the secret nobody tells you in basic courses. The rules are incomplete. They're approximations. They work most of the time, but reality is messier than any equation can capture. And when you're building something new, something that pushes the boundaries, you're going to run into places where the rules don't apply. She would smile, and her students would feel a mix of excitement and nervousness that they could never quite explain. Your job isn't to follow the rules perfectly. Your job is to find out how much you can get away with, to discover the gap between theory and reality, and to build things in that gap. That's where all the interesting engineering happens. 50 years later, the Union's grandest achievement began construction. An artificial wormhole network connecting 12 galaxies, enabling travel and communication across distances that would otherwise take millions of years to cross. The project was led by a joint team of engineers from every major civilization in the Union. Architects provided the theoretical framework, contributed the quantum mathematics. The mechanical priests blessed the designs according to their ancient protocols. And humans were brought in to make it actually work. The lead engineer was a woman named Sarah, granddaughter of. She had grown up hearing stories of the Lattice Project, of the lessons her grandmother had taught the collective about the nature of functional design. She had internalized those lessons more deeply than anyone realized. The wormhole network design went through hundreds of iterations. Each time, the simulations showed failure. The energy requirements were too vast. The spatial distortions were too unstable. The mathematics predicted collapse with certainty. Sarah studied the latest simulation results and made a decision that scandalized the entire project team. "We're going to stop trying to make the math work," she said. "We're going to build a prototype and see what happens." "That is extremely dangerous," the senior architect on the project protested. "An unstable wormhole could consume an entire star system." "So we build it somewhere empty. The universe is big. We can find a spot where a failure won't hurt anyone." The resources required for a prototype of this scale are less than the resources we'll waste trying to make impossible math work on paper. Sometimes you have to build something to understand it. The universe doesn't show you all its secrets through equations. Some of them you have to discover by doing. The prototype was constructed at the edge of a dead galaxy, far from any inhabited systems. Sarah and her team watched as it activated for the first time. Every simulation said it should collapse immediately. The energy levels were too high. The spatial warping was too severe. The quantum fluctuations were too chaotic. The wormhole opened. It stabilized. It held. The readings made no sense. The mathematics could not explain what was happening. And yet, there it was, a tunnel through spacetime that functioned despite every theoretical prediction. Sarah laughed quietly to herself. Her grandmother had been right. The gap between theory and reality was where all the interesting engineering happened. She submitted her report to the project committee with a handwritten note at the bottom, just as her grandmother would have done. "I know it shouldn't work," the note said. "Build it anyway." They did. The wormhole network went operational 3 years later. It connected 12 galaxies. It revolutionized interstellar travel. It made the Union more united than it had ever been before. And every time someone asked how it was possible, how the impossible mathematics had been overcome, the answer was always the same. A human engineer had looked at the rules, decided they did not apply, and built something anyway. That was, in the end, what humanity brought to the galaxy. Not superior intelligence, not advanced technology, not elegant theoretical frameworks. They brought the willingness to try things that should not work, the stubbornness to keep trying after failure, the humility to admit when they did not understand something, and the courage to build it anyway. The universe had rules, humanity had suggestions. And sometimes, more often than anyone expected, the suggestions worked better.